This is section 11.3. We're talking about indirect measurement. We first did a warm-up. We said triangle XYZ is similar to triangle QRS. So if they're similar, that means their sides are proportional. So since I can see that YZ and RS are corresponding, that means they have the same ratio as QR and XY. So we can set that up. Let's make a guide. Let's say the big triangle to the little triangle. It's going to equal, so 20 over 8, that'll have the same ratio and therefore is proportional as 12 to RQ. So let's just call that X. So then if we want to solve, we can recognize we could do 12 divided by 20 and see what we're really, so we could do 20 divided by 12, which is going to be 1.666 repeating, or 1.6 repeating. So I could do 8 divided by 1.6 repeating, and I would end up getting X is going to equal 4.8. Then that's going to have the same ratio as QS and 28. So 28 over QS, let's just call that Z over Z. Solve that. I could even cross multiply if I want to. I could do 20 times Z, so 20Z is going to equal 28 times 8. And then I could do 28 times 8, that's 224, and then divide that by 20, I would get 11.2. Finally, a lot of people got hung up on this. Angle Q is congruent to what angle? And that is angle X. That corresponds. So then we got started with our lesson. We said, how can you measure the height of objects that are far too high for you to reach without a measuring tape or measuring directly? What we're going to do today is measure indirectly using our knowledge of similar triangles. So in class we said, if we have a mirror and a measuring tape but can't stand on anything to reach the clock, how can we determine the height of the clock? So here's our clock. We're standing down here. And we have a mirror. After talking this through, we realized we could put a mirror here, and we could say, well, if you remember, the angle from your eye to the mirror bounces back, or bounces or reflects off the off of the mirror at the exact same angle. So really, we would have to adjust this mirror so that our eye bounces off at the same angle as the clock. So let's see, it would be about here. That looks about right. So our mirror would go right here. So I'm going to erase these lines so we don't get confused. And then we could say, well, we know our height, and we could measure this distance, and we could measure the distance from the mirror to the wall, and we could then find out the height of the clock. So in class, we went ahead and did that, and we said, okay, well, Miss Yetzer, we used Miss Yetzer. I'm 5 feet 6 inches, so that's the same as 5.5 feet. Remember, to figure out that decimal, you do 6 divided by 12, the number of inches divided by the total. And then we measured this, and we said this was about 7.5 feet. And then we measured to the wall, and it was 10.2 feet. And then we were able to find the height of the clock by a ratio. So we said 5.5 is going to correspond to my height, just as 7.5 corresponds to 10.2. And then we were able to solve. So we could solve our ratio by doing 5.5 times what, or we should go the other way because we want to solve this way. So 7.5 divided by what gives me 5.5, so I could do 7.5 divided by 5.5. That's 1.36 repeating, so divided by 1.3, we'll say 36. And that means we have to divide here by 1.36. So 10.2 divided by 1.36 will give me about 7.5 or 48 feet. How many inches is that? That's 7 feet, right? And then 0.48 of a foot, we could do 0.48 times 12. That's 7 feet, 5 and 5.76 inches. So 7 feet, 6 inches, or 7.5 feet. So then we have a new situation. Oops. Sorry. We have a new situation. With John. It says John casts a shadow on the ground that's 9 feet. His height is 5 feet 9 inches. The sign casts a shadow that's 22 feet. What is the height of the sign? So we have two triangles that we can form here. We've got one with John and his shadow that's 9 feet. And we know that the angle from the sun is going to be the same as the angle that's hitting the sign up here. So I'm going to redraw these triangles so I can see. So here's John and his shadow. Then we've got the sign. So that's not really the same angle. Then we've got the sign and its shadow. Here's the signs. And we said the angle from the sun is the same. And we know they're both perpendicular. Therefore, we have similar triangles. So we said this was, his shadow was 9 feet. And John is 5 feet 9 inches. So that's 5, it's not 5.9. We have to do 9 divided by 12, which is going to give me a 0.75. So I'm going to say 5.75. Then we know, we don't know the height of our sign, but we know its shadow is 22.5 feet, or 22 feet 6 inches. So I can set up my ratio now. I could do, this time I'll stay within triangles. So I'll say the little, ratio of the little to the big. So I'm going to say 5.75 over, what corresponds with that, x, is the same as 9 over 22.5. So if I solve that, I'm going to go ahead and cross multiply 5.75 times 22.5. That'll leave me with 129.375 equals 9x. Divide by 9, and I'm left with 14.375 feet. If they wanted it in feet and inches, it'd be 14 feet. Multiply 0.375 times 12, and you get 4.5 inches. Next. I keep forgetting that it's on this document. Okay, the next one. It says, at a certain time of day, a man that is 6 feet tall casts a shadow at about the same time of day. Oh, and at the same time of day, how tall is a tree that casts a shadow of 18 feet? So we have a 6-foot man. He casts a shadow that's 4 feet. At the same time of day, so that means the same angle of the sun, we've got this really tall tree. And it casts a shadow that's 18 feet. I clearly did not draw that to scale. We want to know the height of this tree. So again, if it's the same angle of the sun, we've got similar triangles. So I could just say, okay, well, 6 to 4 is the same as x to 18. I can see, oh, well, look, this is, I could do 18 divided by 4 and realize that 4 times 4.5 is going to have to be the same on the top because it's proportional. So 6 times 4.5 is going to be 27. So I can say x is 27 feet. It's a pretty tall tree. Last situation. Driving through the mountains, Dale has to go up and over a high mountain pass. The road has a constant incline for 7 3/4 miles. So I could write that as 7.75 miles to the top of the pass. Dale notices from the roadside that in the first mile, he has climbed, here's about 1 mile, he has climbed 840 feet. How high does he have to climb? How many feet does he climb in all? So we could set up a similar triangle. Notice that you do have to convert your units to feet. Because I'm saying in 1 mile, he travels 840 feet. So in 7.75 miles, how many feet does he travel? And if you want, you don't even have to use similar triangles. But let's do it since we are talking about that concept, and then we'll talk about it after. So let's convert 7.75 miles to feet. 7.75 miles times, there's 5,280 feet per mile. So that would be, this is 40,920 feet. And in 1 mile is 5,280 feet. So we would set up our ratio. We could say in 5,280 feet, it rises 840 feet. That's going to be equivalent to, in 40,920 feet, how high does he rise? So I can recognize, well, this is just 7 times 7.75, so this will be times 7.75, which is going to leave us with, let's see, 840 times 7.75, which is going to be 6,510 feet. Now you could have recognized that really if it's per 1 mile, 840 feet, there's 7.75 miles, so I could just do 7.75 times 840. But this is just a great way to show that you can use similar triangles to solve a problem. So that concludes our lesson, and you can finish the homework, which is listed on page 599, I believe. Yep, 599, 1 through 5, 7, 11, and 12.